Today we're going to look at two more examples of some improper integrals. The first example we're going to look at is going to be an example where both of our limits approach some type of infinity. So for example, I have the integral from negative infinity to infinity of 6x cubed over the quantity of x to the fourth plus 1 squared dx. Now, when we have an improper integral before and we had only one of these values as infinity, we would find the limit as t approach that infinity and then replace the integral with t. For this case, when we have two bounds of infinity, we're actually going to write two separate limits. I'm going to first start with the limit as t approaches negative infinity. And for this integral, I'm going to take it from negative infinity to 0, or in this case, t to 0. Of that quantity. And then I'm going to create a second integral where t approaches infinity, and that's going to finish up that interval. So we're going to go now from 0 to t for that function. What we need to do now is actually evaluate these two limits separately and then take a sum as our final answer for them. Now, the good news is that we're evaluating the same integral, so we only have to do the work for the antiderivative once and then evaluate the two limits. And in this case right here, since I have this quantity of x to the fourth plus 1 being squared in my denominator, I'm going to evaluate that integral using u substitution. So I'm going to go off to the side over here and do my work for that. So if I'm going to use u substitution, I'm going to let u equal that x to the fourth plus 1. So then du would be 4x cubed dx, and if I solve for dx, du over 4x cubed would be that dx. So now I can go ahead and rewrite this integral in terms of u and du. So for this, I'm going to get 6x cubed. Instead of putting that divided by u squared, I'm going to rewrite that as u to the negative 2. And then the dx would be the du over 4x cubed. The x cubes are going to cancel. 6/4 is going to be 3/2. And if we do the antiderivative of u to the negative 2, that's going to be negative 1 u to the negative 1. So if I rewrite that, I'm going to get negative 3 over 2 times u to the negative 1. I'm going to put that down in the denominator as a positive exponent and replace that with that x to the fourth plus 1. So that would be our value for that. So now what I want to do is use this for the antiderivative, and I'm going to find the limit as t approaches negative infinity for that value evaluated from t to 0. And I'm going to then also find the limit as t approaches positive infinity for that function evaluated from 0 to t. Okay. Now, as we're working through these problems, an interesting thing happens. If we're evaluating this piece and we find out that this piece actually diverges, we don't even have to bother doing the other part, because once one part of this diverges, then the overall integral is going to diverge. So once you do break it up into your two parts, evaluate one part. If it diverges, you're done the problem. If it converges on a number, then you'll actually evaluate the second part and then just add the two values together if you can. So for this one right here, as I'm finding the limit as t approaches negative infinity, I'm going to plug in my upper and lower bound here. I'm going to get negative 3 over 2 times 0 plus 1, or negative 3 over 2 times 1, or just negative 3/2, minus, and then the negative 3 over 2 times t to the fourth plus 1 for that value right there. Now, as I'm letting the limit as t approach negative infinity, this is a constant, so that's going to stay negative 3/2. This negative infinity is going to get raised to the fourth and become a positive infinity. So I'm going to get 3 divided by some really large number. And negative 3 divided by some really large number is just going to go to 0. So this limit right here is going to simplify to just negative 3/2. Since it converged on a value, we're going to actually now go ahead and evaluate this limit using the same type of technique. We're going to get negative 3 over 2 times t to the 4th plus 1 minus the negative 3 over 2 times 1. Again, because we're approaching infinity, this is going to approach some really big number. Negative 3 divided by some really big number, that's going to approach 0. And then a negative times that negative, this is going to give me a positive 3/2. So this limit is going to converge onto 3/2. So since both of the limits converged on values, my final answer is just going to be the sum of those two values, and negative 3/2 plus 3/2 is just 0. The other type of improper integral we can have is where we have an infinite discontinuity somewhere in our interval that we're studying. And for some of the problems that we've been working with, that infinite discontinuity has occurred at one of the endpoints. But for our last example, we're going to look at an example where the infinite discontinuity occurs somewhere within our bounds. So let's say we had the integral from 0 to 1 of 1 over the quantity of 4x minus 1 dx. When we think about this function right here, we know that the denominator can't equal 0, because once we find that value where the denominator equals 0, that's where we get a vertical asymptote. And that causes that infinite discontinuity. So for this function, we're going to get an infinite discontinuity when 4x minus 1 equals 0, or that's going to occur at x equals 1/4. That is somewhere between 0 and 1. So that means that somewhere in between these bounds at x equals 1/4, we have that infinite discontinuity. So what we're going to need to do then is break up the integral into two limits, just like we did up here. And we're going to go from 0 to 1/4 as one integral, and then 1/4 to 1. And since now at one of those endpoints, we're going to get that infinite discontinuity, we're going to find the limit as t approaches the value from either the left or the right. So since we're going to go from 0 to have that break at 1/4, and that's going to give me my first improper integral with that infinite discontinuity there. Since we're going from 1/4 to 0, we're going to be approaching that limit from the left side because we're going from values smaller heading towards that number. And then our second integral is going to go from 1/4 to 1. And again, this time we're having our infinite discontinuity occur on the coming from the right, because we're going to be working with values from 1/4 to 1. So we're working with values bigger than that as we go towards this. So we're going to let the limit, oops, it should be plus, the limit as t approaches 1/4 from the right, from the integral of t to 1. Okay. Now, similar to what we did in these problems up above, we're going to need to evaluate both of those limits. And again, if one of our limits happens to diverge, then the overall problem is finished. To anti-differentiate, again, we need to find the integral of that same function for both of these problems. So if we want to find the integral of 1 over 4x minus 1 dx, we basically, again, can use that u substitution. This time we're going to let u equal 4x minus 1. Du would be 4 dx. So dx would be du over 4. So I'm going to get the integral of 1 over u times du over 4, which is 1/4 the natural log of the absolute value of u, or 1/4 the natural log of the absolute value of 4x minus 1. So that's what we're going to be working with as we evaluate these two integrals. So for the first piece, I'm going to take the limit as t approaches 1/4 from the left of 1/4 of the natural log of the absolute value of 4x minus 1, evaluated from 0 to t. And if I go to evaluate this, I'm going to get 1/4 the natural log of 4, absolute value of 4t minus 1, minus 1/4 the natural log of the absolute value of -1. Okay, now this piece right here, the natural log of the absolute value of -1 is the same thing as the natural log of 1, and we know that that is 0. But for this one here, as t approaches 1/4 from the left, as we're getting these values here, we're creating values that are in here going to approach basically the natural log of 0. And if we think about the values of the natural log of 0, as we're approaching these from the left, we're getting the natural log of these values that are going to be negative. And so if we have the natural log of these really, really small values, this is going to approach a negative infinity. So basically, this is diverging. It's not approaching a regular value. And since this first limit did not exist, it diverged. That means the overall limit diverges, so we don't even have to bother doing that separate limit over there. So our final answer would just be diverges. So in your examples today, you may need to break apart your integral into two values, two separate limits, and evaluate them to see if you can find your final solution.